And did you bring a pencil today?
I did. I brought a pencil last week.
I guess it's you.
It's be able to walk back out of the truck. I wanted you to walk over now.
I was going to send me back to the office, but you couldn't do it. Okay. These are mine now.
That's fine. I don't even like them. Too cheesy.
Next week, bring something you like. I can steal that from you.
No.
I did bring a pencil, but it's probably in the forest of a junk that's in the back of your truck. Okay. I brought my notes, though.
I did too.
Alright, so real quick correction from last week when we were talking about sine and arcsine. Arcsine is the inverse of sine, but we don't use it for what I said. Arcsine is the inverse, meaning that's how you get back to what you started. So the sine of 30 degrees is 0.5, which means the arcsine of 0.5 is 30.
What's cosecant?
Cosecant is the reciprocal, which is
1 over
9 times whatever to make 1. And cosecant is what you would use to get the full multiplier, starting with the.
So we're using cosecant.
Yeah, if you want to save a step. So basically, when you have what?
Caleb, he's sitting there going,
He is lost in the sauce, brother. Don't worry about it.
So the reason you use sine for this is basically just trig from triangle math, so SOHCAHTOA. So sine is opposite over hypotenuse. So just imagine this as a triangle here. So the opposite of the angle is maybe here, and obviously your hypotenuse is here. So what you have is the sine of the angle equals opposite over hypotenuse. So sine A over C, and that'll give you the 0.5. If you just want the multiplier itself, then you would use cosecant.
Why would
Which would instead give you, this would be flipped, so it would be hypotenuse over sine.
Why would we need the multiplier over the normal?
Oh, if you got to do
Because that's like your bend.
Oh, is that like the
degree?
No, you would multiply that.
So the sine of 30 is 0.5.
What am I thinking about? Okay.
Which gives you the times 2 multiplier for a 30-degree bend.
That doesn't have anything to do with the 120 volts to 107.
No, that's RMSLA.
Oh, yeah. Okay. Okay.
I mean, a little bit, because 45 is the... So, dude,
Yeah.
I think
Use of that example.
If we're getting into conduology.
I wanted to make that correction before that set in. I did make a note of it in the description on the video. All right. Is there anything from 2-1, 2-2, and 2-3 that anyone felt like they had questions?
Capacitors. I ain't getting nothing about that. Except the formula.
Okay. I won't bother writing that down. That's the entire section. What?
And inductive reactance. I don't get what the difference between inductance and inductive.
Reactive
is like the equivalent of resistance.
Can you just go over like the terms and explain it
I
in
don't
normal
get, like,
dumb person?
Yeah, we'll go through that. All right, so we'll just go in order.
Like, cause I can read all the stuff that's said about inductance, but like I still don't know what the crap it's talking about. You know what I'm saying? Like,
okay. Anybody else?
Yes. I have 3 textbooks.
huh?
Yeah, what?
3 textbooks. I have VEC Year 2, Electrical Level 1, Electrical Level 2.
It won't even let me log in.
Oh, that's probably the ones that Travis signed you up for. Just Year 2 is mine.
Oh.
I read it.
Anybody else? All right.
Oh, inductive reactance. It's basically the equivalent of resistance because you can't have friction in the conductor, or it's not causing friction.
Two.
Austin, you gotta realize who you're talking to. You're talking to a college dropout.
I'm a college dropout too. What
But
you
you're
mean?
smart.
No, I'm not.
Yes, you are.
I just take diet now.
You just take what?
Diet now.
You got that autistic spark.
That's right. Yeah. Even if I don't take nothing, it's pretty.
Okay.
Ty, what's Ohm's law?
Oh gosh.
Take an ear pot.
Ohm's law. Is that the one with the equation where it's like I over something equals Ohm's?
Ear pot. It's ear pot. One of those two.
Aiden, what's Ohm's law?
Is that the current equals voltage over anything?
That one. Hey, I was kind of close.
Were you?
Relation.
I hope so.
Ty.
That's current equals voltage over resistance.
Okay. How do I get voltage?
How do you use your voltage?
Mm-hmm.
You do.
How do I get
Oh,
voltage?
okay. You multiply. You multiply your current by your resistance. Right?
Ear pot.
So P equals IR.
Yes.
Is he right? Okay.
I'm not dumb.
That's question.
How do you get resistance, anybody?
Resistance, it would be
E
E divided by I.
Smells like a bunch of blue powder in here.
All right.
Yep. It's a little tinted for me. I give you permission to hit him. I don't know what you mean. Would you hit? Whoa.
Hit it fast.
Alright, edit that part out.
No, it's all going uploading straight up.
I worked that out.
Get him off, Striker.
I'm not telling my dad about it. Okay.
All right. So a couple things to remember. When voltage is at RMS value, current is also at RMS value. Everybody remembers what that means.
They're in phase.
It's not necessarily.
Oh, wait. I mean, sorry.
What does it mean when voltage is at RMS value? What's RMS value for?
That is the root mean squared.
Okay, and what does that mean?
That is the average.
Of the area under the.
Yes.
Yeah.
It's the area average of the area under a curve. That's gonna be RMS.
Yeah.
And what is that? What is that value? What is that?
That's the voltage that we get when we put the meter on it.
So when your voltage is at that value, so is your current.
Right, voltage at that value, so is your current.
When
Okay.
your voltage is at RMS, so is your current.
Okay.
All right. So purely resistive circuits. What's in phase in a purely resistive circuit?
Well, what do you mean? What's it face?
What? Okay, fine. Let me rephrase it. What is the relationship with current and voltage in a purely resistive circuit? I just gave you the answer.
They're both in phase and there's no deviation.
Okay. So, since they're in phase, and since the RMS value is usable for both, what does that mean in terms of how you analyze it in comparison to DC?
But you said we weren't looking at DC.
Or not?
DC, you said was a straight line.
You can use the same method. And
You can, yeah.
In a purely resistive circuit, voltage and amperage can be analyzed the same way as DC because they're in phase and RMS value.
What is a purely resistive? Does that mean it's only getting voltage taken out? Probably.
It means the only thing in the circuit is a resistor. The only thing stopping the power from going straight to the source, straight to the ground, is a resistor.
Okay.
So like a light bulb.
Is a resistor.
A light bulb is literally just a resistor. In simple terms, the circuit will act like a steady reading of DC volts at whatever the RMS value is. This is why the meter does not fluctuate between 120 and negative 120 when measuring a receptacle. Ohm's law only applies when voltage and current are in phase. And again, this is only for purely resistive circuits.
Whenever they,
Like in a three basis. I gave you light bulbs. Any other examples of resistors?
Host or
heat motors.
Heaters.
a transformer.
Incandescent orbits.
That's a
Oh yeah, that's a lie. Vacuum tube heaters.
What?
Vacuum tube heaters.
That's still just a heater.
TV.
Only three.
No. Basically, light bulbs, heaters, and resistors. Like just regular appliances.
Do I call him back?
Oh,
It was Dave, but I think he can help.
It's important to call that.
Nah, he gets mad if you don't call.
He hung up in like half a second.
You don't know.
Either way, it's your problem.
Always ask you something.
Okay.
Remember you.
Alright, so when we're doing our work, do we have to take into account the things that are going to be plugged into it? Because we do our math, a lot of the math we do in the field, we do it assuming a purely resistive circuit. It's like when we run our cables to all these outlets, we do the math on all the voltage drop and all of that, assuming a purely resistive circuit. Now, considering how limited the list of purely resistive circuits in the real world are, why do we use purely resistive for all these?
Because it's the easiest way to figure it out.
Because there's a million different things you can plug into a receptacle, right? We can't account for all million plus different stupid things you can plug in. But they know how much power is coming out of here. So they can make their plugs have a transformer, and they take into account their own resistance, capacitance, whatever it is they need in their machine, and have it corrected when it gets sent back out. What's power?
Power?
Mm-hmm. Anybody?
They're rated with the control.
Okay. What is it in electrical terms?
Formula.
Mm-hmm.
Power is equal to the dissipation. Current
times
times
voltage.
Current times
voltage.
What were you saying?
Oh, I thought you were talking about dissipation.
What's the unit of measurement?
Watts.
Joules?
Oh wait, no, just watt point or volting.
It's watts or volt amperes, depending on what context you're using.
Mark.
All right, so we already have Ohm's law, and we already know that in a purely resistive circuit, which is what we're working on right now, current and voltage are both in phase and directly proportionate. So this allows us to find true power using substitution. So we start with pi. We start with
Ohm's law. Ear.
and this is
Ear. Ohm's law. Oh, like you mean to say what it is?
Yeah.
Oh. Voltage equals current times resistance.
okay. Got, and I just told you power is current times voltage. So how can we fit this in here to give us power?
You can do P
Where are the current?
equals
E equals
I squared times R.
well, you're skipping a step. So what we're doing is
Oh, you can tell you what
we're
I'm
going
doing.
to substitute
Substituting E.
that E
E
for
for
this
I.
E. So what we get is I times I R.
Which is the same thing as I squared, correct?
Yeah.
but you
So
okay.
so true power equals current squared times resistance.
Yeah, I do.
Any questions on how or why we got there?
So that one false power.
True power is also known as RMS power. That's funny. Kai, what's dissipation?
Dissipation
Mm-hmm.
is that the amount of resistance? Is that what dissipation is? The amount of resistance in a oh gosh, in a insulated conductor?
I think the resistance is the amount of resistance in an
The amount of there's a word I'm missing. Hang on. Hold up.
Austin, would you like to show up that?
What am I doing?
Dissipation. What is it?
Just energy being lost.
Sort of. Dissipation
The rate.
is the portion of electrical energy that is actually consumed by the load and converted into useful work, such as heat or mechanical energy.
So the used up voltage.
Yes. Well, not voltage per se, but the electrical energy.
So power.
What kilowatts?
All right, we good?
Yeah.
All right, go to figure 10 in the textbook. I don't have These notes are from before I started filling down paperwork, so
In year
you
10.
just have to find it. Mm-hmm.
Okay, this one.
Okay, well, that's it.
So are those are still in sync, correct?
And pay.
Because or in phase.
Yes, they
they're
That was going to be my first question. Yes, they are in phase. Does the amplitude matter? And will it cause problems if the amplitudes aren't the same?
between E is energy and I is current. No, it should.
Okay. What decides the amplitude of the voltage? What is the amplitude of the voltage? What is the X value? Or sorry, the Y value? Anybody? I'm gonna try both.
What is time?
No, the Y.
Oh, just the beat.
Okay, so the value of the voltage, right?
Yeah.
So the strength of the value of the voltage depends on the strength of the voltage applied to the circuit. It's not as complicated as it
I know.
sounds.
That's why I'm sitting here like confused.
It really was that easy. Yeah, the voltage is whatever voltage you put in the system. Yes. Not every question. Not every question is a brain scratcher.
Yo, Mar.
What decides the value of the current?
It's what some they current. The
The amount of current applied to the thing. So smart.
Yeah.
You go apply current to something,
Yeah.
it has to do with the amount of voltage
Resistance.
applied to that
and
Resistance.
resistance.
there you go.
No, that.
Maybe if you all take the test together, you'll pass it.
We got
No, she.
Yo, Omar. I don't got my courses available for some reason.
First you go.
Did you have it before?
Mm-hmm.
Go to.
Are you sure you
go to
signed
my
in?
go to my labs instead of that.
I had two.
My labs.
I had two different sign
Do I have
in.
to develop a different
I
website?
signed in.
Yeah, Google Pearson My Lab or something like that.
Pearson. My. Oh, you're so smart, Omar. You see my YouTube comment?
Did you see my phone?
Inductive AC currents. The life of me, I don't know why I put 27 pages worth of notes here.
Yeah. Huh? I got like 30.
All right. Inductance.
Don't.
Inductance is the creation of a voltage due to a current that changes over time.
How often are our tests?
Each module has a test.
How many modules are there for this year?
Yes, I told me I had a quiz today.
Or actually, I think it was 11.
So roughly 1 a month.
One of the Warners told me I had a quiz today. I was like, no, it doesn't.
Maybe they did.
Oh well, no, because some of the modules are longer or shorter than others. Gotcha. Well, you okay?
Is there a conduit bending? Like module?
Conduology? Oh, yeah, we get into some conduology.
And you guys are going to find out you don't know shit about bending conduit.
Hey,
Hey, I learned from the greatest.
Dude, Holmes Law.
Rocky.
I learned from Holmes Law on YouTube.
Holmes Law.
Yeah.
Holmes Law. Rocky's motto. If it don't look right, it ain't good. If it looks right, it's good.
In my
If it's
the
above
only
the
person that taught
ceiling,
me
it's
how to
fine.
make conduit
Is that all there is to induction or inductance? Sorry.
No.
No, because you wouldn't be asking that question if there was.
Need a better answer than that, Ty. That is technically correct.
It has to oppose to change of current.
It doesn't have to oppose the chain of current. It is the resulting opposition.
Yeah, Austin.
You didn't know that?
I did. I was just trying to be humble.
Me too. Yeah.
So, inductance is both the creation of a voltage due to current that changes over time, and the resulting opposition of to the current change. So it's measured in henries, which is
Henry's?
yeah,
Oh, gosh.
which is just a capital H. Can you have induction with a DC circuit?
No.
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 Right.
You wouldn't be asking me if there was. You could.
Circuit. You had to call them.
Oh, for all the YouTube viewers right now, that water was given to Amar by me.
You know, I got like
So all
5
the
4
thousands and millions
right
of
here.
viewers know.
How many push-ups y'all think you can do?
A lot more than you.
And you're like,
I did so many.
I could probably do rip out 20 if I had to.
Okay.
Why?
Just wondering how many questions you can afford to get wrong,
On what?
or you do push-ups.
Huh? I'm sorry.
Every time you give me a smart ass answer, like no, because you wouldn't be asking otherwise you're doing push-ups.
But it wasn't wrong, so you can't punish me for a wrong answer.
Telling everyone that you have 2 turns into boot camp.
All right. So because it's a response to the change, that means one's gonna lag and one's gonna lead. So between voltage and amperage, which one lags, which one leads?
Voltage
Voltage
probably
lags.
leads.
No current.
Current legs. And voltage leads.
Mm-hmm.
How's that?
Because the so induction,
But the
is,
voltage is created by the current.
they create each other. So, but
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 that
it
says the
starts-
creation of voltage due to a current
yes,
that changes.
yes. So the voltage coming in, because you don't send current somewhere, you send voltage. The current comes later.
The current is determined by how much power your device is pulling.
At any given point,
Like a
current is potentially infinite. That's why shit explodes when it gets short circuited.
I have fault current
You know,
ratings.
at any given point, the only thing stopping anything in here from drawing infinity amps is the OCPDs and the resistance, like the various resistances and reactances in the circuit. That's why when it connects directly to the ground, it blows up because it pulls. So it pulls in. It tries to pull in infinity amps, and then whatever is carrying it, either the OCPD trips or the thing explodes because it took too much power. It got too hot. So voltage first, and then the changing voltage creates the current.
All the time.
Let me see.
Is it
I know I have this in a section. I'm just trying to see if I want to do it now.
The camera's still on.
My telefono.
Hey guys, 420. Time for it.
You're fired. You know my birthday's on 420, right?
Same as Hillary.
I know, and it's a National Weed Day. I explained it to my siblings yesterday. They never knew that, but they didn't stop laughing for like an hour.
We should just dress up.
The sad part is,
One day.
I hope my parents never watch this video. But the sad part is
I'll email it to
when I told them that it was National Weed Day, they thought I was talking about weeds in the yard, not marijuana. I tried to explain to them it was marijuana.
So you have well, you need green. You have your conductor.
Mm-hmm.
Inside your conductor, you have your voltage traveling through. Problem is, I kind of covered some of this stuff last week, so now I'm.
Let's just go straight on the train.
All right, so basically, the AC in the conductor, because it's changing, it has a rate of change that creates a moving flux. So back to the magnets, it basically creates a magnetic field around the conductor, and as the voltage goes up and down, the magnetic flux also pulses, so in and out with the voltage. And so now you have a moving, so basically now you have a conductor technically cutting across magnetic lines. So the conductor is not moving, but the magnetic lines are. But the effect is the same. You still have a conductor cutting across magnetic lines. So what does that create?
Friction.
We did this last week with the generator. When the conductor cuts through the flux, that creates
Current. But
you turn the camera around and that'll help you. Trying to hide from it.
I've hide from him. Thanks.
Huh?
The horse has screwed.
Yeah, I farted like 20 minutes ago.
There you go. So, did you watch the video, Caleb?
no.
Okay, well, it'll make more sense if you watch the video. There's a lot to go over, so I'm sorry I can't really double back to explain all that now. So, watch the video, watch this video, and then next week, we'll be addressing things again. All right. So, the voltage creates magnetic flux. Magnetic flux creates voltage. So, that's why. So
Which comes first, the chicken or the egg?
the voltage comes first. It's the
No,
voltage.
the conductor comes first.
All right. This moving flux cuts across conductors in the circuit, including the one providing the current, and induces voltage in the wire itself. So we touched on this in the first class, but this is why we separate different strengths of voltage and why we don't run communication cables with AC.
What was it up here?
Oh.
Now, here's a question: if you have DC and you have it running, it's running at 10 volts, and then it jumps to 40. Is there induction in there? in that conductor?
No, because it's caused over change of current over time. But that's just
Change of
that's
current,
an instant jump though.
Time.
But it doesn't
Instant jump.
go across time;
There's
it
a-
just goes straight up.
That's
Voltage
really
was
fast.
induced into
For that split second, there was voltage induced in this system.
I think it said that it did cause induction whenever it changed.
It does. And anytime there's a change in voltage, there's a accompanying reduction. That's just voltage and change. Now, obviously, like from this point on, no.
Yeah.
This instant, yes. So. AC always produces induced voltage, and lower frequencies require more inductance to produce the same amount of induced voltage as higher frequencies. Questions? Tell me what I just said, Ty.
Lower frequencies require more inductance.
What was the rest of that sentence?
Oh, you were writing.
Pay attention.
I am.
Lower frequencies require more inductance to produce the same amount of induced voltage as higher frequencies. Why? Anyway,
the amplitude's greater on the higher frequency.
not necessarily.
Well, the magnetic field's stronger.
Inductance is decided by the rate of change.
Mhm.
So if something has a higher frequency,
That's
and it changes more often.
gold star.
The ability of a conductor to induce voltage into itself when the current changes is referred to as self-inductance. That's pretty self-explanatory. The symbol for inductance is yes. And the unit is still a Henry.
Henry is it?
All right, now here's a sentence. 1 Henry is the amount of inductance that allows 1 volt to be induced when the current changes at the rate of 1 ampere per second.
Yes, a lot. Yeah, that means.
Now it sounds complicated, but think of it this way. You all know what a calorie is, right?
Yeah.
You understand how a calorie works. Ty, look up the textbook definition of a calorie and read it out loud.
You'll say PPE.
What?
Great notes. Well, that's when you get a lot of calories.
Everyone except Ty gets to play Mario Kart.
A calorie is a scientific unit of thermal energy defined fundamentally as the amount of heat energy required to raise the temperature of 1 gram of water by 1 degree Celsius at 1 atmospheric pressure, while colloquially used to measure food energy. This definition represents the small calorie, whereas nutritional calories are actually large calories.
Okay, so you heard that complicated ass definition of a calorie. You don't need all that. You know what a calorie is. It's basically the same symbol here. So 1 Henry is the amount of inductance that allows 1 volt to be induced when the current changes at the rate of 1 ampere per second. So
Oh.
1 volt induced at a rate of 1 ampere per second. That's it. So volt seconds over amperes. Yes, no.
Watt?
Definition of
No,
inductance.
watt? No, I'm sorry.
I feel like not everyone's getting that, but no one's asking questions.
I mean, it makes sense.
Okay. What was it?
H equals B times S over A.
Okay.
I knew you could ask that. So I looked at it really good before you missed it.
Alright, what is it now?
H equals B times S over A.
What does it mean?
Mr. Henry equals
If that's what it takes me to remember it.
the amount of volts times seconds
Mhm.
he can work in a great amount of amperes. Is that right? Amperes.
Sure. We gotta come with that actor.
The amperes he talks out.
Dude, this class would be like way Mark explain everything and Clash Royale tournaments.
No.
Dude,
Put Mega Knight in.
dude,
I
if
would-
you could explain
I would walk
induction in
around.
terms of a Mega Knight, that'd be a fire. Like,
We should add
Something
that
that
into
like
the-
Pico.
yes. Hold on.
The
Great
voltage is like
idea,
peaking
thought.
when you upgrade your town hall to level.
I'll ask you about capacitance.
Factors affecting inductance. The inductance of a coil or inductor depends on its physical construction. So, what are the aspects of the physical construction that make it?
Heat.
The number of carry.
Ooh. Number of turns, coil diameter, length of core material, winding the coil in layers.
Every once in a while, you impress me. Every once in a while.
Bro, I said it at the same time we did.
Who impresses
Yeah, but I
you?
expect it from you.
Who impresses you more, me or Aiden?
Hey man, I saw myself.
I have higher hopes for you, so you disappoint me.
I told myself.
I was kind of surprised you said that.
That's great.
No offense to you, but you just kind of like la 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 la, and then like spark of brilliance.
It's not accurate.
I have to like really, really understand something like entirely and really well for me to understand like the other parts of it and stuff, and I'm just like,
All right, hit me again. Number of turns.
coil diameter. Coil diameter.
Length of core.
Thank you, Ty.
Core material.
Winding the coil in layers.
Like that.
Can't believe ChatGPT actually did this.
Capacitance equals elixir storage.
Huh?
Think of capacitor
Yeah.
like your elixir bar.
It's not
It
great.
doesn't do damage or push by itself. It stores energy, elixir. So it can be released when needed. Charging a capacitor equals waiting for elixir.
Did you ask?
Yes, and it makes so much sense.
When you're not playing cards, your elixir bar fills up. In a circuit where voltage is applied, the capacitor charges up, storing energy. More voltage, stronger pressure to fill it. Like double elixir time. That makes a lot of sense.
Does it really?
Yes, it actually does.
Capacitance measured in
Or
bar
children.
quads
It doesn't make
equals
any sense.
max
It's even
elixir
worse.
capacity. Actually. A small capacitor is like having a deck where you can only hold 5 elixir. Okay. large capacitors like holding 10 elixir store more before it's full. Higher capacitance equals more charge stored at the same voltage. Discharging a capacitor equals dropping a big push. When you place a card, elixir drained into the capacitor discharges it releases its stored energy in elixir. Example, capacitor equals an LED. You can see a quick flash, like dropping a tank.
Okay,
We're all-
enough.
Hey,
I can't listen to this anymore.
you want to hear about factors affecting inductance in Clash Royale terms?
No.
I do.
The number of turns equals a skeleton army. The iron core is a Mega Knight or a golem. The core
Your
material-
ChatGPT algorithm is so retarded, bro.
The core material is either a tank versus a squishy troop.
Okay.
Coil size. is the
I'll set
arena
aside
supply.
a day. We'll have a review day, and the entire review day will just be you guys taking the class in terms of Clash Royale.
But you gotta start playing Clash.
Absolutely not.
I go like a look.
An inductor is a defensive building.
Okay,
that
enough.
I got my elixir. Another year two guy.
Sorry.
Now you gotta wait till year two.
All right. Number of turns. How does that affect inductance?
What did you say?
How does the number of turns affect inductance?
It increases inductance when you have an increase in the.
Greater number of turns, the greater the inductance.
Okay.
The spacing of the turns in the coil also affects.
All right. So more turns,
More inductance.
more inductance. All right. How about coil diameter?
The inductance increases directly as the cross sectional area of the coil increases.
The Clash.
You can't take my phone. It's in the test.
Plus, have your own now. Throw your notes.
In the truck.
This is his.
No, it's not. That's my
We got. Log.
my actual notes are in the truck down
Some
there.
elegant artwork
Show
right
the
here.
camera. Show the camera.
And the Milky Way galaxy.
No, yeah, that's a cool. It's okay.
The
Oh, I
page
see.
previous is my budget.
You should see that.
See, if you're lost, what helps is asking questions.
That was at the beginning of the class. I was trying to be retarded.
Are you still lost?
No.
All right. Coil diameter. We don't have to go super deep into it. Just plus or minus turns, plus or minus inductance, or plus or minus diameter, plus or minus inductance.
Plus plus.
So more diameter, more inductance. Length of the core.
The shorter, the higher,
Why?
because there's less cross section. Well, no, there's just less area.
So if you make the diameter, if you make the diameter bigger, you make the core bigger, it increases inductance. If you make the core shorter, you make it smaller. So does that increase or decrease inductance?
It increase
Why does it increases instead of decreasing it?
because
becoming
the
larger.
turns is greater.
Because it's what?
Becoming large, right? There's more. The diameter is bigger and the number of turns
There's
is more.
less cross sectional.
So
No, the length of the core. The length of the core.
Less area.
This way or this
Turn
way?
spacing is.
Diameter.
It's more
I guess the
concentrated.
ratio.
It's more concentrated.
Hang on, we're focusing on tie right now. What you're trying to say is correct.
Sorry, I was
The
paying.
length of. Okay, back up a minute. Are we talking about like on the inside of it? Okay, I just wired up a transformer. A trans was like you have your leg coming in, your leg coming out. One of those, is that what we're talking about? Where it's got a bunch of copper coils wrapped around?
Sort of. Sure. Part of it.
You're talking about cool.
Is that like what we're talking about though? Like, is that what
Yeah.
that would describe? Okay.
Yeah.
So the length of core, what is the length of the core?
All it is.
How long? What is like the
But
core?
the core.
The middle? Well, it would be more because you've got a lot more turns. The longer it is, the more time it's going to take.
The only thing that's changing is the length of the core, nothing else. So if you only increase the length of the core or you only decrease the length of the core, everything else stays the same. Number of turns, everything else is the same. So it's going to,
Let's say increase, but I don't know why.
so if you increase the length,
What the? What
it actually
material is
decreases the inductance.
Why?
So again, you're only changing this. Everything else stays the same, which includes number of turns. So if you make this longer with the same number of turns, the turns are further apart.
Uh-huh.
And if you make it shorter with the same number of turns, the turns are
Closer
closer
together.
together. And as we know here, how close they are.
Gotcha.
Okay.
Okay.
All right, so core material. I'm just gonna give you this one. Coils wound on magnetic material produce a stronger magnetic field, increasing inductance. So, plus, more magnetic it is, the more induction it causes. And then closeness to turns.
The closer they are, the more inductance.
Why is that?
More concentrated.
Yeah. So when you have
You did on the.
Gosh.
Well, I can't even see the board.
Just what we want to see.
Hit that button right there. Upside down.
So
First ready when you need
Soon. Hang on. Back up and I'll
hang on.
turn that off.
You gotta
Turn the smart composition off. I'm so smart.
it's just doing it.
No. It'll follow you, but it won't zoom in or out.
I don't want it to follow me either. There's no reason for it to follow me.
Oh my god. But man,
Whoa, you can do that with your hands? Turn all that off then.
Jarvis,
You can do this to zoom
my screen.
somehow. Don't move. Just don't move.
So if you have your core, then you have your coils around it. If they're spaced out pretty far, when the AC runs through them, they create their fields. They may be so far away that they don't even interact at all. But when they're piled up right next to each other,
Their amplitude increase.
then now every time it's interacting multiple times,
Having two ways together.
Yeah, basically. So it's like you have the field created by one conductor. And if it's by itself, it doesn't interact with anything but itself. Now you put two, now they interact with each other. Double up. Three, they all interact with each other. And so on and so forth.
Would it be uniform or like you said, like 3 or 2 together? Like
I mean, for this, it's all one conductor. It's all one continuous.
I'm saying the coils though, would they be all evenly spaced apart?
Yeah, they should all be evenly spaced. Then.
In theory.
That was it.
444.
445.
All right.
No, I said 444.
We'll take a break then.
Oh. That computer is 1 minute behind.
Bro, you gotta tell him what Matthew said about the. Dude, that's so funny.
But what?
Dude, I was.
Hang on, before you say something, I was gonna get this.
Uh-oh, who brought?
Number one.
Let's turn off the mic.
We're experiencing technical difficulties.
You pause it.
We have
Technology.
I can only stop it, which I don't really want to have to stitch it back together. But
Starts going live. Hey guys.